Good evening, ladies and gentlemen. It is my great honor to welcome you to the 14th Gerhard Ertl Lecture. My name is Gerard Meijer. I am the Managing Director of the Fritz-Haber-Institut of the Max-Planck Society, and I extend a warm welcome to all our attendees at the screens. It is, unfortunately, I should say, already the second time that we have to do this event virtually, with the advantage that in this way it is more accessible for a broader audience. I would like to welcome our honored emeritus, Professor Gerhard Ertl, Nobel Laureate, and the reason why this award came to existence, as well as Professor Omar Yaghi, this year's award winner. Furthermore, very happy to welcome Dr. Detlef Kratz from BASF, Professor Sabine Kunst, President of the Humboldt-Universität zu Berlin, Professor Christian Thompson, President of the Technische Universität Berlin, and Professor Günther Ziegler, President of the Freie Universität Berlin. And we have also been joined by the award committee, comprised of our jurors, Professor Joachim Sauer, Humboldt University, Professor Matthias Dries, Professor Gerhard Ertl, as well as the Fritz-Haber-Institut's Board of Directors. I welcome you all. We're celebrating a long tradition of Nobel Prize awards in our society. Already the founding director of our institute, Fritz Haber, has been awarded the Nobel Prize in Chemistry in 1918 for the ammonia synthesis, and the legendary Albert Einstein worked at the institute for some time as Haber's guest. And no less than 8 Nobel Prizes in physics and chemistry have in total been awarded to members of this institute. Most recent one was awarded to Professor Gerhard Ertl in 2007, who was director at the FHI for almost 20 years. Professor Ertl carried out exceptional research in the field of catalysis, surfaces, and interfaces, which is the reason why our prize honors outstanding personalities and researchers in these particular fields of physical chemistry and chemical physics, as we will see later on in this lecture. And actually in front of me, there is a book that came out this year where Gerhard Ertl has described his life in science that I would like to recommend to everybody who is interested in that. But also in these days, currently, we have special reason to be proud to be part of the Max-Planck Society. Because just on Tuesday, here in the Harnack House, just around the corner, 2 scientists of our society have been honored with the Nobel Prize in Chemistry and Physics, Benjamin List and Klaus Hasselmann. Outstanding science is only possible in an international context with worldwide collaboration and networks. So it is my great honor to introduce this year's winner of the Gerhard Ertl Lecture Award, Professor Dr. Omar Yaghi from the University of California in Berkeley, United States, who joins us from his home at the west coast of the United States, and of course also from quite a different time zone. It is now 7 a.m. in the morning Pacific time. So good morning to you, Omar. Good morning, California, everybody who's watching from there. Professor Yaghi is a distinguished scientist, professor of chemistry at the University of California in Berkeley since 2012. He received many international awards. For example, in Germany last year, he was awarded the Medal of the German Chemical Society. The first time I personally met our lecturer was 2 years ago, at the end of October in Oslo. It was during the Norwegian Academy of Science Conference, Chemistry 2019, on Odd Hassel's shoulders to commemorate the 50th anniversary Chemistry Nobel Prize for Odd Hassel, who coincidentally also did his PhD research at our institute. And I was extremely impressed by the talk that I then heard from Omar Yaghi on the atom, the molecule, and the framework. More recently, in October of this year, Omar Yaghi announced a new research success in the journal Science, together with Professor Joachim Sauer from the Humboldt University. As we all know, drinking water is becoming increasingly scarce in many regions of the world. And that is why this American-German research team has been working for years on methods to harvest water from desert air. Porous metal organic materials play an important role in this. Water molecules from the air get caught particularly well in their cavities, and now the team has analyzed the molecular chemical processes of water harvesting and optimized the materials that can be used to harvest water from dry air. Will this solve the world's water problems? Maybe we will hear more about this interesting research project during the lecture. Omar, I would like to once again congratulate you, and I'm very much looking forward to your lecture about reticular chemistry and precision reactions in infinite 2 and 3D. And before we start with your lecture, there will be still some other presentations, but at the beginning of that, I would like to officially hand you the document that goes together with the Gerhard Ertl Lecture Award. And strangely enough, you have it already. It is standing behind you as well, so I could give it to you like this, right? And then you grab it there on the side and you show it maybe to everybody. So this is how that works nowadays. It is the official document announcing that you have been awarded the Gerhard Ertl Lecture Award, and we're very, very pleased and very honored to have you here today. I already want to inform everybody who is listening to the presentation now, everybody who is sitting at the screen, that there will be a question and answer session after Professor Yaghi's talk. And you're welcome to ask the questions that arose during the talk. Please ask the questions in the chat. And somebody here will then actually ask the questions in person to Omar Yaghi. So you can formulate the questions already during the presentation. But before we're going to listen to your presentation, Omar, I would like to give the floor to Professor Sabine Kunst, President of the Humboldt University Berlin, for the welcome speech. And after that, there will be Dr. Detlef Kratz, President of Process Research and Chemical Engineering at BASF, will speak out the laudatio. For now, I give the word to Professor Sabine Kunst.
Thank you, dear Professor Meijer, dear Professor Ertl, esteemed award committee, dear colleagues, Professor Ziegler and Professor Thomsen, dear Dr. Kratz, ladies and gentlemen, and of course, dear Professor Omar Yaghi. It is an honor to welcome everyone today to this virtual awards ceremony, the 14th presentation of the Gerhard Ertl Lecture Award. Thank you, Professor Meijer, for your introductory words of welcome. As Humboldt Universität, we are proud to have been a part of this honorary event, which was gained quite a prominent standing in the scientific community since the beginning. In 2008, the Lecture Series Award was established to celebrate Professor and 2007 Nobel Laureate Gerhard Ertl for his outstanding achievements in the field of surface chemistry and heterogeneous catalysis. It was also established to praise and applaud excellent researchers continuing this important work in the field of catalysis, which is why we are all here today. Today, the 14th Gerhard Ertl Lecture Award will be granted to Omar Yaghi, the James and Neltje Tretter Chair Professor of Chemistry at the University of California, Berkeley, elected member of the reunited U.S. National Academy of Science and a pioneer in the new field of reticular chemistry. His work of designing and synthesizing materials at the molecular level has not only gained him the position of being among the top 5 most highly cited chemists in the world today, it has also propelled a number of important applications. One of the more recent examples is the optimizing of metal organic frameworks for harvesting water from desert air. This exciting study has just recently been brought forward by a team of researchers consisting also of Professor Joachim Sauer from our university. Collaborations like these are at the core of what pushes science and industrial research forward. The Fritz-Haber-Institut and Humboldt-Universität, as well as the other representatives of this award, FU, TU, and BASF, have a long history and tradition of collaboration. Since the founding of the Fritz-Haber-Institut as a part of Max-Planck-Gesellschaft, then called Kaiser-Wilhelm-Gesellschaft in 1912, researchers from both worlds, academia and applied science, have made fruitful contributions to each other's work, which honorary professorships, international cooperation, and student exchanges between our institutions we have learned from each other and will continue to do so in future. Let's return to the most important topic of the day, to you, Professor Yaghi. I'm very impressed by your scientific achievements. I congratulate you and wish you great success in the perseverance of your outstanding scientific activities. I'm very much looking forward to your lecture on reticular chemistry and precision reactions in infinite 2D and 3D. Before we hear your lecture, I would like to hand over to Dr. Kratz.
Yes, thank you very much, Sabina. And I would like to continue with the laudatio of today. So, dear Professor Yaghi, dear Professor Ertl, dear Professor Meijer, Professor Kunz, ladies and gentlemen, everyone on the screens. It is a great honor for me also to introduce our speaker for this year's Gerhard Ertl Lecture Award ceremony. Already everyone has seen him now, Professor Omar Yaghi from the University of California in Berkeley. And I'm delighted that you, Omar, are the 2021 recipient of the award. As already mentioned, unfortunately, this is the second time in a row that we cannot hold the awards ceremony in person, because I think everyone would have loved to have been in Berlin. And who would have imagined that the COVID-19 pandemic would force us for a virtual format like this again? But that's a pity, but let's make the best out of it. Now, the jury has selected Omar Yaghi in recognition of his pioneering work and great accomplishments in the fields of reticular chemistry. And I quote the jury here. They said, with his discovery of indefinite 2- and 3-dimensional metalloorganic frameworks and covalent organic frameworks, Professor Yaghi created the basis for the new field of reticular chemistry, which links molecular building blocks by strong bonds into crystalline extended structures. They go on to say, this new chemical space enabled him harnessing precision chemistry and important applications, as he has shown, for hydrogen storage, carbon oxide capture, and harvesting water from desert air, as we have already heard. Ladies and gentlemen, before I continue to introduce Omar and his achievements, let me start by telling you a little bit about the award itself and how BASF is involved with it. The Gerhard Ertl Lecture Award was first presented in 2008 by a number of institutions, the Freie University Berlin, Humboldt University, the TU Berlin, the Fritz-Haber-Institut, UNICAD, and BASF. And it is dedicated to one of the most prominent scientists in the field of surface chemistry and heterogeneous catalysis, the Nobel Laureate, Professor Gerhard Ertl. Now, this accolade is presented by partners from the worlds of academia and industry in recognition of distinguished individuals and researchers in the field of catalysis. And this year, we are presenting the award for the 14th time. And I think I can rightfully state that the Ertl Lecture Award has gained standing in the scientific community. Progress in catalysis research is hugely dependent, among other things, on how well we know the surface structures of carrier materials and which reactions take place on a molecular basis. And the understanding of the exact catalysis mechanism is at the heart of everything we want to draw conclusions about structure-property relations from, and further to develop materials. And that is why both universities and research institutes provide significant input into terms of fundamental findings and method development. But only the next step, the transfer of these findings into commercially available products and processes, will push science forward as a whole, as well as accelerating industrial research. And if we look back over BASF's more than 150 years of history, this is exactly what we have been doing from day one. Right from the start, BASF has been carrying out its own fundamental research while supporting others to do so. Collaborations with academic partners have always played a vital role in our activities and contributed immensely to our work. A prime example is, of course, the development of the ammonia process and catalyst about 100 years ago together with Karlsruhe University. And we have continued in this spirit, and that is why we founded BASCAD, a laboratory run jointly by UNICAD and BASF at TU Berlin in 2011. And it is mainly tasked to generate fundamental knowledge in the area of new catalytic processes. And in this context, I would also like to mention the CARA collaboration. CARA stands for California Research Alliance and is a multidisciplinary research institute of BASF, together with the University of California and other renowned US West Coast universities. And it's Omar Yaghi, who is a founding member of this alliance and one of its directors. At CARA, we combine basic research with industrial research and have done so successfully since 2014. And Omar, this is also where we met not too long ago, actually just before the COVID pandemic set in, and I had the honor also to hold a talk through a screen because it was exactly at the beginning in March 2019. But let's move back to the most important topic today. Let me talk a little bit more about our awardee, about you, Omar. Omar Yaghi was born in Amman, Jordan, and, encouraged by his father, he moved to the US at the age of only 50. After finishing the college, Omar, you started studying chemistry at the State University of New York, Albany, and then the University of Illinois, Urbana, where you received your PhD in 1990. Followed by an NFS postdoctoral fellow at Harvard University, you started your research as an assistant professor at the Arizona State University. And in one of your numerous interviews, you explained that you wanted to do something completely new and not pursue scientific approaches that already exist. And that led to the idea of building new structures by strong bonds using the building block approach to make open frameworks. And many scientists at the time challenged you that this could not work. But, Omar, you have proven them wrong. And that is very much true to your saying, and it's a quote now, if you can think it, you can make it. And that was the birth of a new class of compounds known as metal organic frameworks, the so-called MOFs in short. And that's how it is with visionary approaches. First, you had to convince the academic community of your idea. And then, with your first article in Nature, which is titled Design and Synthesis of Exceptionally Stable and Highly Porous Metal Organic Frameworks, which was published in 1999, such a proof point was made, and the community set up and took notice. A new material, you call it MOF5, with an inner surface of almost 3,000 square meters per gram. This seemed to be incredibly high and exceeded everything that was known before. And at the same time, the crystallinity of the material was unexpectedly low. And it was a year later, in spring 2000, that you first met Ulrich Müller. By the way, he's also on the call, who was a BASF expert of zeolites at the time and also up to his retirement. And at that time, a sample of 20 milligrams of this MOF exchanged hands. And that constitutes the starting point of a long-term and truly fruitful collaboration between you and also BASF. Now back to your academic career, Omar. You took position at the University of Michigan and the University of California, Los Angeles. And since 2012, you held 3 titles: the James Annett Tretter Chair Professor of Chemistry at the University of California in Berkeley, followed by the co-director of the Kavli Energy Nanosciences Institutes, as well as already mentioned, the co-director of the CARA collaboration we have. And starting with your first visionary approaches back in 1999, the field of MOFs has extended incredibly since then. The number of publications has increased from 68 at that time to more than 7,000 in 2021. A similar increase is valid for the number of patents. And the Cambridge crystallographic dataset now counts more than an amazing 100,000 structures in this field. And doing research for academic purposes is one thing, but the next level is to commercialize these findings into various applications. The properties of the MOFs, such as gas storage, were shown to be the door opener for the logistics and transportation sector. Gas separation of carbon dioxide, for example, could support the sustainability approach, and water harvesting might result in a low-energy air conditioning techniques. Now, these applications raised the interest from startup companies, and around 20 of them are on the way to launch products on the market based on MOFs, and Omar, you are highly engaged here as well. And please allow me to make a side remark at this point. At BASF, just recently, we managed to produce a MOF structure out of the family of MOFs for a customer in a several ton scale. This is truly the next step in commercialization. Now, ladies and gentlemen, Omar Yaghi has received numerous accolades for his outstanding scientific achievements and for his expertise in metal organic frameworks. The Materials Research Society Medal in 2007, the King Faisal International Prize in Science in 2015, the Albert Einstein World Award of Science in 2017, the E&I Award for Excellence in Chemistry in 2018, and the Grigory Amenov Prize by the Royal Swedish Academy of Sciences in 2019, and recently the August Wilhelm von Hoffmann Denkmünze of the German Chemical Society, and many, many more. Omar is a fellow of several societies, holds several advisory and editorial positions, and is an elected member of the US National Academy of Science. Let's look at some more numbers. Omar, you have documented your results in more than 330 peer-reviewed publications, many of them in prestigious journals such as the Nature 8 and in Science 23. The number of total citations is higher than an amazing 158,000 with an H index of 156. You have given more than 400 invited talks at conferences, including more than 120 plenary and keynote lectures, and more than 31 named lectureships. You are involved in 60 patent families, and these all are really impressive figures. But this is by far not everything. Mentoring, coaching, and empowerment is very important to you, Omar. You have supervised around 200 postdocs, PhD students, and visiting scholars. Many of them now hold academic positions in various ranks. And at the end of my speech, let me focus a little more on mentoring and teaching, which really goes to the bottom of your heart. You are the founding director of the Berkeley Global Science Institute, whose mission is, quote, to build centers of research in developing countries and provide opportunities for young scholars to discover and learn. And you said you know from your own biography how much mentoring can contribute to the start of a scientific career. Your engagement in the Berkeley Global Science Institute is your way to give something back to what you have received in your early days. You share your knowledge, your techniques, and your strategies to your students without any conditions, knowing very well that they will follow their own career path and might be your peers and even competitors maybe in the future. And at the same time, you mentioned that teaching and being a mentor is always a two-way interaction. You learn how your students think and thus get ideas from them and develop them further. You call this the sustainable part of global science. Dear Omar, I'm really impressed by all of these scientific achievements. And now it is my pleasure and a great honor to welcome you today to our virtual awards ceremony. We are very much looking forward to hearing your lecture entitled Reticular Chemistry and Precision Reactions in Infinite 2D and 3D. And I would like to hand over and the screen and the floor is yours. Thank you very much.
Thank you.
Maybe a few words also from my side in between. Thank you very much, Professor Kunst. Thank you very much, Dr. Kratz, and for these nice words. I want now to indeed give the floor to Omar Yaghi. I think after this long introduction, we're all very eager to hear what you have all been thinking about and what you have made based upon that. Omar, the floor is yours.
Thank you all so much for these touching words. Detlef, thanks for this generous introduction of me. And Gerard, Carsten, Sabine, it's really a pleasure to see you and to listen to you. I am so honored to receive this lecture award, the Gerhard Ertl Lecture Award for 2021. It's really a pleasure at many levels, including the fact that Gerhard is one of my idols since I was a student. And I met him when I was a student. He probably doesn't remember me, but it was a memorable meeting at one of the Gordon conferences. I want to talk about reticular chemistry. This is an emerging chemistry, and I want to show you how we can precisely put together building units to make infinite 2D and 3D structures. Before I go on, I really want to acknowledge Sandra and Brigitte for the flowers, the tastefully done flowers that I received yesterday. Thank you very much. And let me show this. This is quite a memorable picture of a surface, a metal surface, onto which you see oxygen binding to the surface. This is what Professor Gerhard Ertl has taught the world, and these are images that are imprinted on every student's mind because of the power of the atom on the surface and the impact that that has on reactions. So the question that I want to ask today is that could we prepare substances where all the atoms in that substance are a surface? From Gerhard Ertl work, we know that an exposed atom has a lot of chemistry and a lot of power in affecting unusual reactions. And today I want to show how we can answer this question. How do we make every atom in a substance a surface? And that's what reticular chemistry offers. It takes the image that is here on the left and turns it into a structure that looks like the one on the right, the Escher drawing of primitive cubic, where the atoms are stitched together to make a porous structure, but where every atom, as I'll show you, potentially can be an adsorptive site and accessible, and therefore the entire material, all the atoms in that material, is a surface. So this is reticular chemistry. This is really the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. Molecular building block, there are three components, I would say, in this definition that are very important. Molecular building blocks, because we want to be able to design structures from well-defined building units. And strong bonds, we want to stitch them together by strong bonds because we're interested in making durable materials that can withstand, let's say, taking up CO2 from air year after year after year without having to be replenished or maintained, so that they can be cyclable and durable. Crystalline is another component of the definition that's absolutely essential, and it's the progress that has enabled reticular chemistry, is to be able to link building blocks through strong bonds and still make crystals rather than amorphous structures. Crystalline provides at least two very important contributions to reticular chemistry. One, obviously, like the surfaces that Professor Ertl was working on, being crystalline and well-defined. Here, crystallinity provides us a way to characterize our materials on the atomic and molecular level. And also, as you will see with water harvesting, it plays a major role in plucking out water from desert air. The result of reticular chemistry has been metal organic frameworks. And unlike any other metal organic structure preceding these MOFs were made from negatively charged linkers, such as terephthalate, linked by metal ions, in this case, a tetrazinc unit being linked by the carboxylate. This charged linker, the negative charge on carboxylate, and its bonding to the metal ion produces a strong bonding, in some cases as strong as carbon-carbon bonds. So we showed in 1995 for the first time that Metals linked by anionic linkers such as carboxylates could be made as crystals. In fact, I would say this was the beginning of MOF chemistry. That's where we coined the term metal organic frameworks. And in 1998, this strong bonding and the ability to assemble multiple metal ions and use them as corners or as intersections in a network showed that, in fact, this arrangement could produce architecturally robust structures, as evidenced by the very first gas adsorption isotherm made on a metal organic material. And this gave us the porosity parameters that allowed us in those days to compare our materials with well-established materials such as carbon, porous carbon, and metal oxide and zeolites. I will show later, in 1999, we showed how this strategy, using MOF5 shown here, can produce ultra-high porosity. The next development in reticular chemistry came with covalent organic frameworks. These are materials that are stitched together by entirely covalent bonds between organic molecules, and there are no metals involved in these. In 2005, we showed for the first time that we can make 2D structures, and in 2007, we showed that we can make 3D structures. And more recently, we demonstrated molecularly woven COFs. And these combine the robustness that I'm talking about of the strong bond with the mechanical interlacing of threads so that you can make a woven, one could call it a woven fabric, again with molecular precision. This provides you with the robustness that one needs in a material, but also the flexibility of that the interlocking of these threads provides. At the end, it provides with superior mechanical properties for these solids. So the way to make a MOF hasn't changed much from what we reported in the mid-1990s and in this report in 99 for MOF5, which is to take an organic acid, deprotonate it by, in this case, you have DEF, which has base present in it when heated, and that base deprotonates the acid, and then the carboxylate reacts with the zinc to make an extended structure. The key development here is that we figured out the reaction conditions under which to crystallize this structure, which is entirely linked by strong bonds, carbon-carbon bonds, carbon-oxygen bonds, and oxygen, or one can say negatively charged oxygen oxide and metal ion, in this case zinc, to make this extended structure. And we use the yellow ball to indicate the space within which other molecules can go in. So this synthetic conditions that you see here are still in use today in making carboxylate-based MOFs with slight variations here and there. But as Detlef mentioned, my friend Ulrich Müller came to me after I had given a zeolite Gordon conference or a zeolite conference in Germany, and thought that perhaps this surface area could be a misprint in our publication. This was back, I think, at the end of 99, beginning of 2000. And in fact, he said that they were trying to reproduce MOF5 and that it would be nice if I can send them a sample. I sent them a sample, and indeed they got the surface area that we obtained. In fact, BASF number was higher. And in our lab, our numbers hovered around 2,900 meters square per gram. And in the hands of Ulrich, that surface area was around 3,000 or 3,300. Nowadays, because we learned how to evacuate the pores of MOF5, the surface area, the optimal surface area is close to 4,500 meters square per gram. So you see here the gas adsorption isotherm, typical type 1 isotherm with sharp knee, fully reversible, and it's done as the gold standard for porosity at 77 Kelvin and low pressure. So this set the field on an expansion course The extremely high surface area broke all records of porosity for 1,000 years that was held by porous carbon. And now we have materials where, as I will show shortly, every atom is an adsorptive site. So MOF5 is very special in its architectural robustness. And that's because if you look at, this is the crystal structure of MOF5, and if you look closely, you find that the terephtalates are actually at 90 degrees to each other. This is 90 degrees to this one, in that they turn 90 degrees with respect to each other. And they also, of course, have these 90 degrees. And that's the best way to build a structure, even if you were trying to build a building. These are the sort of interactions that you want to maximize to build a robust architecture. And that's exactly what we have in MOF5. And notice here that this is not very much unlike the Escher drawing that I showed you before. The structure is very open, and the nice thing is that if you know the reaction conditions under which to produce this multi-metallic unit, which we call secondary building unit, then one can add the linker with the desired functionality. And in so doing, you're functionalizing the pores. So you're taking a crystalline material and now you are deliberately fashioning the pores for a specific property and a specific application, as well as one can expand the pores to make progressively larger and larger pores so that larger and larger substrates could be manipulated and controlled in the pores. So to really show where is this high surface area coming from, we took a crystal of MOF5, you see it here, and put it in a capillary and cooled it down to 30 Kelvin. In most materials, especially porous materials, will lose their monocrystallinity when you cool them down at 30 Kelvin, not MOF5. Even though the crystal was completely evacuated and cooled down 30 Kelvin, it maintained its monocrystallinity. And this allowed us to take for the first time a crystal structure, single crystal structure, using X-ray diffraction of the framework without anything in the pores. Here you see an article with 90% ellipsoids of the framework of MOF5. Very well behaved atoms and they can be determined with precision. You see here one of the adsorptive sites without anything in the pore has absolutely no guests. So you see the electron density of the atoms representing the metal oxide unit. However, as you add argon introduce argon or nitrogen, you see the electron density of argon settling in around the adsorptive site, which is on the metal oxide unit. So does nitrogen. Okay, these experiments allowed us to figure out what are the adsorptive sites within MOFs, and then understand why they have such a high surface area per gram. And you see here that all the yellow dots you see here are either argon or nitrogen. And you see that everything you're looking at in a MOF is an adsorptive site. The faces of the octahedron, the edges of the octahedron, as well as the faces of the tetrahedron of zincs, they're all adsorptive sites, and all of them were determined, including the faces of the six-membered rings, as well as the edges of the six-membered rings. All of these, we found argon atoms interacting with them as adsorptive sites. And we also went beyond the monolayer and localized some of the argon atoms and nitrogen that are filling the pores. So what this study does, it says that everything you're looking at in a MOF is an adsorptive site. And so we needed to even go beyond the surface area of MOF5. And so we designed this structure from a trigonal organic units with the same SBU as MOF5. And you see that's the surface area is 6,400 meters squared per gram. And so the very first thing to know about MOFs is that they're all the atoms are surface atoms. And they have pores, but the pores do not have walls like other porous materials. So they're entirely, can be thought of as scaffolding, and that's why they have extremely high surface area. But also the fact that the pores have no walls allow substrates to move in and out of the pores with great facility. And that's another great advantage of MOFs. So you can see that this then became a worldwide activity. Almost every metal in the periodic table has been utilized to make MOFs from the various SBUs, some of them discrete and some of them even extended SBUs, rod SBUs. All can be linked by organic linkers ranging from lactic acid, citric acid to terephthalate, simple or eco-friendly linkers to very long linkers such as this 11-phenylene unit linker. They've all been made into MOFs, either in my lab as in this 11-phenylene unit or in other labs as you see here. A great variety of structures could be made from a great variety of linkers, of organic linkers. So this is where I always say, if you can think it, you can make it. This is the beautiful thing about this chemistry, is that it works. You can make crystals and from assembly of these organic linkers and other organic linkers like them with a variety of metal ions in the periodic table. So let me show you what the future offers, I think, for MOFs, at least in one direction. Since Professor Ertl is interested in catalysis, I want to share this result with you. Here we have a MOF that is made from rod SBUs that are linked by organic. And we can functionalize the rods or the linkers so that they have NH2 units onto which one can add. In this case, we're adding amino acids to make a short chain amino acid peptide, a short peptide into the pores. Okay, and one thing to keep in mind, and this is, some of you may feel very uncomfortable with this, is that when you run a reaction inside a MOF, unlike molecular chemistry, if your reaction is not 100% complete, then you have the converted functionality as well as the unconverted functionality or the partially converted functionality. They're all encompassed within the pores. So the pores at the end, when you're doing, as in this case, 7 different transformation, protection, deep protection, since these reactions are not 100.000% complete, then you have what I call a multivariable environment, meaning that you not only have these short peptides made from 4 amino acids, but you also have the shorter versions and the incompletely converted functionality. It is, you can think of it as a forest of different functionalities, okay? Some you want and some, from a traditional point of view, you don't. You can think of them as impurities, but to us, they are opportunities to decorate the interior of the pores with heterogeneously arranged functionalities. We call them multivariable functionalities. The backbone is ordered and is unchanged, but the interior is full of heterogeneously arranged functionalities. And the power of this heterogeneity is that a substrate floating through the structure could sample nearly an infinite number of environments. And therefore, one can affect very selective reactions. So here's an enzyme, TEV endoprotease, and this enzyme, you can see here the different functional groups decorating the mouth of the enzyme, and it's programmed basically to cleave this amide bond. and only this amide bond. No other material could do that. But now with the functionalization that I just described, approximating the amino acids that decorate the mouth of the enzyme, you can see that our multivariable environment can cleave exactly the same bond. So I think this is saying two things. One is that the multivariable environment does not all have to be fertile for this bond cleavage. You only need enough microenvironments to code for this amide bond cleavage. And the rest of it could be, does not have to be necessarily involved. But the power is that the substrate is sampling millions and millions of microenvironments until it finds the right arrangements. And so I think that there is a lot of potential here for developing catalysts in using this multivariable approach. And so in a way, by having a multivariable environment, we have in a way optimized in a combinatorial way a microenvironment that will carry out a selective operation. I'd like to just say that the active site of an enzyme is extremely heterogeneous. When you look at it, it has many different functional groups that are arranged in many different ways. When metals are present, they are arranged, they have different coordination, very odd coordinations. And so it's not very much unlike what we think is the interior of these multivariable MOFs. So that's sort of a quick tour through some of the developments in original developments in MOFs. Now I want to go to COFs, and I like sharing this statement written in Scientific American by Roald Hoffman back in 1993, where he says that organic chemists are masterful at exercising control in 0 dimension. One subculture of organic chemists has learned to exercise control in 1 dimension. These are polymer chemists, the chain builders, but in 2 or 3 dimensions, it is a synthetic wasteland. Okay? Basically, he's saying there's absolutely nothing in terms of infinite 2D and 3D organic structures, covalently linked organic structures. And so, unfortunately, I didn't discover this article until much later, after we have invented COFs. I wish I discovered it earlier when I was assistant professor. I would have included it in some of my proposals. But the reason that there is nothing is that if you do embark on linking organic molecules together through covalent bonds to make extended structure, this is the sort of extra powder diffraction you're going to get. You're going to get a hump like this that you can't do very much with. It's very poorly crystalline product or even amorphous solid. And so our idea was, let's look at molecular reactions and perhaps, for example, here's a boronic acid, and it's known in molecular chemistry that dehydrating boronic acid, you get triboroxine anhydride. And this is a planar molecule. If you look at the crystal structure, there's a very weak CH oxygen bond here, hydrogen bond, that keeps this molecule planar. And so our idea was, if we do diboronic acid, we should be able to make this structure, and in fact, you can simulate the extra powder diffraction for this structure. But of course, going to the lab and making this in crystalline form was another story. It took us many, many years to finally arrive at the conditions under which one can allow the extension of the structure to become a crystal and control the kinetics and thermodynamics of crystallization. And what allowed us to do that is that this reaction has as byproduct water, and we run it in a sealed tube. And by controlling the pressure of water in that tube, you can control the reversibility of this reaction and therefore be able to control the crystallization of the material. And of course, the solvent system that you use is absolutely essential. So are the temperature and how long you wait for the crystals to form. These turn out to be the magic conditions under which almost every COF that comes next is made with very slight variation. But the idea is to control the pressure in the tube by also controlling the polarity of these solvents. So that did the trick. And so that hump that I showed you before, now for this material, you see sharp X-ray powder diffraction. And this is a simulated X-ray powder diffraction. You compare it to the experimental one, and this gives you an initial model to solve the crystal structure. We also do spectroscopy to confirm that the bonds that are linking these molecules together do form. And from NMR, we can also do the same, in this case, boron 11 NMR, which gives us information about the yield of the polymerization or of the reaction. So this COF is basically has a graphitic structure where the layers are slipped with respect to each other, but this is the first 2D extended structure made entirely from covalent bonds. One can also do this in 3D using reticular chemistry principles. You use a tetrahedral unit, you dehydrate that. Notice that the conditions haven't changed much aside from just lower temperature, and you make an extended structure made from triangles and from tetrahedra. And that happens to be this one. We call it COF 108 in 58% yield, and it's the lightest solid known to date, I guess after lithium at room temperature. So it's a very porous structure made from light elements connected by covalent bonds. This is the calculated X-ray powder diffraction. This is the experimental one that we can obtain the structure from. So that's 2D and 3D covalent organic frameworks, and this set off, of course, a worldwide activity in racing to make other COFs from other linkages, such as in our case, we extended this chemistry to imine linkages. And here you see we got rid of the acetylene and added acetic acid so that we can enhance the reversibility of this reaction during formation and get crystals. We can make the expanded version of that, again, under the same condition, except with a little bit more acetic acid. And this was the crystal structure of this COF was done from electron diffraction, collaboration with Professor Zhao Dongzhu, University of Stockholm, and it revealed that the structure is 9-fold interpenetrated. But this was the very first time one can get a single crystal structure of a COF. And so this was very exciting because now we can have COFs not just characterized by powder diffraction, but also by single crystal and therefore know exactly the atomic arrangement within the structure. Of course, the ultimate in making robust materials is to make carbon-carbon bonded materials. And so here you see how we are able to make olefinic materials that are linked by double bond, carbon-carbon double bonds. And so here in the original conditions are there, but we added acetonitrile trifluoroacetic acid at a slightly higher temperature. But you make this beautiful structure that the temperature is not so high as not to allow these organics to survive, but low enough that you can preserve the character of the organic, which is something that you need later in terms of functionalizing the structure. The structure looks like this. It's a slipped graphite layered structure. And as we did before, we look at the IR and NMR, both carbon-13 and nitrogen-15 NMR to characterize the connectivity, as well as we use a diffraction, X-ray powder diffraction to confirm the structure. Notice the stability of this structure. This is the original COF 701 X-ray powder diffraction. This is the material in 12 molar HCl. This is the material in saturated KOH in water. This is the material with N-butyllithium, methyl lithium. So it's a very robust structure. And this is very important for water harvesting or for carbon capture properties in making robust materials that can work year after year after year without having to be replenished or regenerated in terms of their structure. Now, a lot of the structures that we have done in COFs over the years have been from powder diffraction. And very recently, we discovered a way of adding aniline, something BASF is very famous for, adding aniline to control the imine exchange in the structure and therefore control the crystallinity. If you're patient and you can wait many, many days, you can also get single crystals of COFs. These are shown here. As you see here, as you increase the amount of aniline in that particular COF synthesis, so does the size of the crystal. So 100 micrometer crystals of covalently linked extended 2D and 3D structures are now possible. And so not only is the synthesis done with precision of molecular chemistry, but now characterization is done with the precision of molecular chemistry. But instead, we are doing it in infinite 2D and 3D. So did we get the structures right? For the most part, we got them right from powder diffraction, but there are certain things we didn't get right. For example, we couldn't decipher the water structure within this COF. So you see water chains that we could not see, could not fully appreciate from the powder diffraction. And so, yes, there's a lot of value in getting single crystal structures, and that's why it's the holy grail in materials characterization. You can also make structures that you couldn't predict. For example, when you link tetrahedra together, usually you make cubic diamond topology or COFs that are based on the cubic diamond. But in this case, you make the hexagonal diamond structure, which without a single crystal structure, we couldn't have characterized it. So I would say that COFs now are on a very strong basis, both in terms of the reaction conditions and the characterization methods. And that's why the field is now one of the fastest expanding fields in chemistry. But we can move forward with our ideas of making unusual materials, and I just want to show you very quickly molecular weaving. Here, if you ask a student to make this COF structure made in this way or of this kind, of course they'll just ignore you. But a reticular chemist think about this in the following way, is that in order for me to make this structure, all I need is a molecule that has this crossing. If I can make a molecular building unit that has this crossing, then using reticular chemistry or COF chemistry that I just showed you, I can link these together and manage to make a woven structure without actually having to weave threads in and out of each other. So that's exactly what, in the end, what Yuzhang Liu was able to do. She took this mutually embracing complex that Jean-Pierre Sauvage used to make catenanes, but instead of catenanes, she functionalized it with aldehydes, copolymerized it with the diamine to make, as you can see here, threads that are weaving in and out of each other, and brought together at regular intervals by the presence of the copper to make a woven structure. And if you don't want the metal there, you can remove it by adding KCN to make the completely woven or completely organic structure. This also can be reversed by adding copper. Since the threads are woven, they do not get let's say, unzipped. And so this process is quite reversible. Turns out that the woven structure has tenfold more, let's say, increase in elasticity compared to the one that is metallated. And that's what we're looking for. We're looking for flexible materials that can retain the robustness, but can carry out dynamics. More on that in future. This is the extra powder diffraction of the metallated. This is the demettallated. Obviously, you lose crystallinity, but you don't lose the structure. So the material is not amorphous, it's not crystalline. And you remetallate to regain the original structure, which means that the threads are still interlaced and have not gotten unzipped. Like a lot of COFs, we try our best using electron diffraction, in this case, both X-ray powder diffraction and electron diffraction to fully characterize the material. This was done in collaboration with Yahan Ma, Shanghai Tech, and Professor Osamu Terasaki. So this is what the structure would look like idealized. Because the threads are actually, in this structure, they are helical. So it's a lot simpler to see it in this way. But you see here the threads weaving in and out of each other. Okay, so based on what I have been saying, we can now take building units. If you've got well-defined molecules and you can determine their geometry, you can assemble them. And we have a table here that tells you which structures you should be able to come up with, okay, based on the symmetry of those building units. And this can go on and on with progressively more and more complex building units. Fortunately, some of these have not yet been made, which leaves enough room for the emerging scholars to plug into this area. But you can think about any one of these boxes, and there's infinite amount of chemistry that could be done, not just in terms of the size of the building units, but also their composition. So, and that's why this chemistry just is so extensive and so popular around the world. Because it's easy to make these, relatively easy to make them, and if you can imagine a structure, potentially you can go to the lab and make it successfully. Okay, so in the last, let's say 5 to 10 minutes, if I could, I want to give you an example of how these materials are being used and studied for carbon capture in water. I don't think I'll have time to discuss hydrogen today, but I will discuss very briefly carbon dioxide and move on to water. The problem for capturing carbon dioxide can be divided into two challenges. One challenge is from point sources. Depending on what a power plant burns, the amount of CO2 in the flue gas could range from 5 to 16%. In air, it's 400 ppm or 0.04%. And so capturing carbon dioxide from air is a lot more challenging because it's very dilute. So this is where MOFs can, I think, try to address this challenge. So you need high capacity, you need a material that's water stable. Now you see how every atom being a surface becomes very important for high capacity. And you see how my emphasis on the strong bonds and covalent bonds become important when you talk about water stability, oxidation stability, cyclability, and we need to keep our eye on the regeneration temperature and make sure that that is lower, not higher, since that's energy that you have to put into the system. Well, here's a list of all kinds of materials that are being investigated today, including MOF. There's carbon, zeolites, MOFs, hydroxides, carbonates, amine liquids, and so on. I won't go through this slide, but I'm just showing it to say that there isn't an ideal material yet, unfortunately. But maybe I'm a little biased. I think MOFs have so many handles of control over their structure that they're beginning to show some promise. So I'll show you one such structure. Here's a MOF made from zirconium cluster. And this cluster has formates on its girdle. And on the other sides, it has those linkers that go on to form the structure. And it's these formates that are on the girdle that could be substituted in a solid-to-solid transformation, substituted with amino acids. The amino acid has a carboxylate on one end, in this case glycine, so carboxylate on one end and an NH2 unit on the other end. The NH2 unit acts to selectively bind CO2 from air or from flue gas. And this is, I just want to show you how one can take a MOF, let's say, and use it as a molecule, in that you can carry out precision reactions on very specific sites on the cluster, so that now instead of formate, you have glycine. That's what we have done. And then tested this material for uptake. So we have set up a prototype where MOF 808 is the sorbent here, and we expose the material to a wave of gases. In this case, this is simulated air with 400 ppm CO2. And you see here that the outgoing air has only 0.02 millibar of CO2. So a significant reduction of the majority of the CO2 from air. And from flue gas, where let's say you start with 15% CO2, again, all of these are under practical conditions. You can get the flue gas cleaned up from CO2 down to 2% CO2. With a regeneration temperature, depending on exactly what you're doing here with the flow rates, it ranges from 40 to 90 degrees Celsius, much lower than what you would use in the aqueous amine solutions. So we're not there yet in terms of overall capacity of the MOF, but we definitely have a way to trap CO2 before it reaches the atmosphere from flue gas, and bind CO2 from air. So this is something that we are actively pursuing in collaboration with GE at this time. So finally, I want to show some results on the water harvesting. I probably need not tell this audience about the water stress that the world faces, but these regions that are not in yellow are considered water stressed. And almost 1/3 of the world population lives in water stressed region. The UN projects that by the year 2050, almost 5 billion people will be affected by water stress. And even in the watered regions of the world, the purity of water that we're getting in our kitchen is uncertain. We always have questions about that. So, and third factor is national security factor for some countries, especially since 160 countries import their water or depend on another country for their water. So even regions of the world where we think have plenty of water, like the Midwest of the US or the East Coast, they're projected to have water stress in the year 2040 because we're using much more water from underground than is being replenished. So fortunately, and my point of view is that there's plenty of water in the air. There is almost 13,000 cubic kilometers of water in the air at any one time. That's as much as we have in rivers and lakes on the planet. So could we use this resource like we pluck CO2 out of the air? Could we pluck water out of the air? And before any of you tell me that I'm going to dry the air that we breathe, I just want to say that you could serve each person on our planet 50 liters of water every day, and you would have only used less than 0.001% of the water in the air on that day. So there's plenty of water in the air. Now, the idea of harvesting water from air is not new. It's been around since time immemorial. And in fact, you could buy instruments that allegedly takes up water from air. They claim that they can take it up from air regardless of the weather, but in fact, they only work at humidities higher than 60%. The rest of the time, or the rest of the humidity range, they don't work. At lower humidity, where it's most needed, these do not work. The reason they don't work is because in order to get water using these equipment, they rely on cooling, direct cooling of air. And so let me explain why that's not, I'll explain that in 1 second. But before, I just want to say that if you could make a MOF that works in the red region of the world, then that same MOF could work even in the watered regions where the water may not be pure. So the vision that I've had is, could we harvest water from air anywhere in the world at any time of the year? And I think if you could make a MOF that works in the desert, you should be able to achieve this vision. Now, this is the problem. Okay, this is a psychrometric chart plotting water vapor in air in grams per cubic meter versus temperature. And let's imagine that I'm in a city where the the arid climate. So I have a relative humidity of 20% at 30 degrees Celsius. In order for me to use the cooling cycle, let's say to get water out of that air, I have to cool down that air down to 4 degrees Celsius. Well, that's energy intensive. That's like refrigeration. So that's not a viable way of harvesting water from air. But if I have a MOF that can take water out of the air, out of this air, at relative humidity of 20%, I could concentrate water in that MOF and in a closed system, create a humidity. And from that humidity, I only need to cool down a few degrees to get the water out. Okay, that's how MOFs work. And there are other systems out there that are being used, like zeolite and polymers and hydrogels and molecules, molecular crystals and salts. But in order to have a viable material, you need high capacity. So the idea of every atom being a surface becomes even more important. You need fast kinetics. The openness of MOFs allows you to go in and out with great facility. And you need a system that binds water at low humidity. So the way we discovered water harvesting from air was during our experiments with studying the interplay between CO2 and water, since when you're binding CO2 from air, you also bind water. And we discovered that for this MOF 801, which is a zirconium MOF, the isotherm for water was very unusual in that it took up water at relatively low humidity. So this is around 20% relative humidity, and took lots of it in a sharp isotherm. And we can take the water out at 45 degrees Celsius, so at relatively low temperature. So this gave us the idea that you could go to the desert with this MOF and trap the water from air at night, and then during the day when it heats up, you could remove the water from the pores and condense it. And so this was really the vision, and I'll discuss more about that in a second, what we've done with that. But before, we wanted to show that, in fact, the water can go in and out with great facility. And so we did, at the time, we did around 80 cycles with absolutely no imprint left on the MOF, and that the MOF is stable. Except we saw that after the first cycle, that there's a drop in capacity. And so we wanted to know what's going on in this. And so now the crystallinity of MOFs becomes really important. And so we looked using single crystal X-ray diffraction and neutron diffraction at the very first water molecules that go into the pore. And we find that they bind to the metal oxide unit. As you see here, the red is basically the oxygen of water to make tetrahedral structures and cubic structures. And it is these structures that are bound to the metal oxide unit that act as seeds onto which other water molecules will hydrogen bond to build what I call chunks of ice inside the structure. And that's why you see that sharp knee behavior in the isotherm. That's an indication of a cooperative interaction between the water molecules and these seeds. So these seeds, in a lot of the discussion that we have on water harvesting, these seeds stay in the MOF, and that's why we're only taking in and out of the pore only the water molecules that are bound to those seeds and not the seeds themselves. So we wanted to show that this works outside the lab in real environment. And so we built a first generation water harvester made from a box within a box. The small box has the MOF basically, and the outside box at night it's open. So desert air goes into the MOF. MOF takes up water, gets saturated. During the day you close the outside box, and in the sunlight it heats up. And as the water vapor hits the walls, it condenses and you can collect water. And so we took this to Arizona. This is what the box within a box looks like. It's fairly simple, just 2 plexiglass boxes. But this is now you can see the condensation on the walls of the material, and the students took this, as I said, to the Arizona desert and were able to harvest 200 to 300 milliliters of water per kilogram of MOF. Okay, so this is a success. The MOF works in the desert with no energy input aside from sunlight. Okay, so basically you can, in a rudimentary way, you can just have a bucket of this stuff in a corner and you can harvest water, you can make drinking water. This is as much as a small bottle of water. And it turns out that we're not using the entire MOF because our MOF was used as a cake. So air wasn't able to diffuse all the way down through the entire cake. And so there was a need for modifying the form factor of the MOF. But the water you get is ultra pure. It's just distilled water. And you can't really drink it on a routine basis. You need to mineralize it. But this student sent me a video of him drinking the water.
All right, ready, 2, 3, action. Cheers. Nice.
Eugene is living and thriving. He's very happy. He has graduated from my group and continuing to work on water harvesting as part of a startup that we have here in Silicon Valley. But the beautiful thing about reticular chemistry is that MOF was a zirconium MOF, and zirconium is expensive. So you can go back and design a MOF, in this case, a rod SBU MOF from aluminum, using this linker to make this structure we call MOF 303, made from rods that are arranged in parallel and linked by this organic linker. And this MOF works even better than the zirconium MOF. I want to point out that if you're a molecule floating in the channels of this MOF, you'll see that the nitrogens of your linker are pointing towards each other to make what later you'll see is a hydrophilic pocket. And the next pocket is a hydrophobic pocket. So you have alternation of a hydrophilic, hydrophobic, hydrophilic, hydrophobic throughout the structure. And so we took that MOF, and now we use thin films in cartridges. And just for the interest of time, I'll zip through this. These are the results from the Mojave Desert, where we took 1 kilogram of MOF 303. In this case, we interfaced our device with a solar panel to allow us to have power to push air through the material. So this is a powered device that's going to allow us to do more than 1 cycle per day. So here you see the humidity in the Mojave Desert when we're in the experiment. During the day, it goes down as low as 5%, 7% relative humidity. And during the night, you have higher humidity. Okay, and this is, whether it's day or night, you are harvesting water. You can see here, the students came back with this video showing dripping of water as the device is cycling through, taking up water from air and using the power, heating up the MOF to release the water and then condense it. So from that experiment, we harvested 1 liter of water per kilogram of MOF per day. Okay, and that's using a little bit more of the MOF. Still, we're not using the entire MOF material. I just want to emphasize, this is a kilogram that now has been tested over 30,000 cycles. So it stays in the device for the lifetime of the electronics, around 5 to 6 years, delivering 1 liter of water per kilogram of MOF at very low humidity range. So the beautiful thing about MOF 303 is that it releases water with great facility. Okay, so you can see here that within less than 3 minutes, I can desorb all the water. And this allows us then to go to another water harvesting prototype that cycles through many cycles during the day. So this is a device that can take up water from low humidity, and it goes in through cartridges of MOFs. They take up water, you can see condensation there. And then these are the cartridges rotating. While one is taking up water, the other one is releasing water. The water is being accumulated here at the bottom and collecting water. This device used only 200 grams of MOF, and you can get 4 liters to 5 liters, depending on the weather, 4 to 5 liters of water every day. But I emphasize 200 grams of MOF that can stay in the device for at least 5 years. Okay, so in finishing up, I just want to show that we have made a lot of progress in achieving what should be the ultimate capacity of the MOF, which is 100 liters. Right now, we are hovering around 80 liters per kilogram of MOF per day. Well, the MOF works in the desert at 5 to 7% relative humidity. It should work in the Atacama Desert, even at the driest desert in the world, driest time of the year, you can still deliver about 4 liters per kilo. And this is the Mojave Desert, but you can see in various locales around the world, regardless of the weather around the year, you are delivering water. And so the vision of water harvesting from air anywhere in the world at any time of the year should be possible with MOF CO3. Here, in some of the more humidified region, you can see that we can take up over 80 liters per kilo, while in some of the very dry regions like Los Angeles or Riyadh, you can take 40 liters of water per kilo per day. Okay, so the last thing I want to cover in just one slide is where are the water molecules going? And this has been a very nice collaboration with Laura Gagliardi and Joachim Sauer, who have worked with us on determining where the water molecules are residing in the MOF. So this is an experimental effort as well as a computational effort. And here again, you see the hydrophilic pockets and the hydrophobic pockets. And I'm going to skip over just explaining everything in detail. I just want to tell you that every water molecule that goes inside this MOF, we have located, especially the very first water molecules, we have located experimentally, and the computation predicted those even before we did the experiment. So you see here, these are just the water molecules going in at different phases: seeding phase, clustering phase, and networking phase. So I'm just going to show the movie now. And it's going to go into one pore, and then slice the pore in half so that you can see where the water molecules are going. 3 water molecules will bind to the framework itself, to the nitrogens, and then those are the seeds onto which other water molecules will bind and build up the chunks of ice inside the structure. The amazing thing that Joachim Sauer and Laura and our group are coming into is that we think that the way the first water molecules sit in the structure determines the density of water that builds up in the pores. So there is more to this story to come. It's a very, very exciting study, and it shows the power of being able to not just construct MOFs with precision in 2D and 3D, but also to determine with precision where the water molecules that we're going to drink are residing into the pores. Once you know where the water molecules are, then you can start making pinpoint changes, turning the nitrogens into an oxygen or the perazolate into a furan, and controlling how tightly the water molecules are bound, and therefore controlling the temperature at which water can be evolved from the structure. So I'm going to just end here and remind you that if we served 50 liters to all 6.7 billion people, to each one of them, we would have only used just 0.002% of the water in the atmosphere at any given day. So ultimately, what we're trying to do with water harvesting is that we want the water to be distributed, mobile, off-grid, personalized, The water is pure, so you can use it for drinking upon mineralization or for agriculture or for household purposes. But ultimately, my vision is that for the world to achieve, or for the individuals to achieve water independence. So finally, I want to acknowledge my current students, and in addition to those that I've acknowledged during my presentation, the funding sources, and I want to thank you very much for your attention, and it's been an honor to be the Gerhard Ertl Lecturer for 2021. Thank you for this prestigious award, and if I haven't done so already, I want to thank the selection committee for choosing me. Thank you. I'm happy to answer any questions.
Thank you very, very much, Omar, for an absolutely spectacular presentation. It's also interesting to see that during your presentation, we all saw the sun come up in California, whereas here it got darker in the meantime. And indeed, we thought that in this case, we would enable some questions to be asked. We will keep it short, but if there are questions, actually, there's a group of people, small group of people that is listed as presenter. If they would have a question, they can switch on the microphone and ask the question as such. For me, it is very difficult to moderate that. And the other people who have asked a question via the Q&A, via the chat, Karsten Baldauf will actually then ask this question because he has been controlling that at the computer. So if somebody would like to ask a question from the presenters, please speak up and introduce yourself and speak up.
Okay, if that is not the case, then I could simply, sorry, was I jumping you now, Martin?
Yeah, maybe I jump in. And so I'm Martin Wolf, one of the directors of the Fritz-Haber-Institut, and I just have a very practical question. So if you have these devices in the desert and you have, how sensitive are these MOFs, for example, to environmental issues like dust and or small dust particles and so on? It looks like everything works out extremely pure and clean, and the desert seems to be not such a clean environment to me.
Yeah, so far the MOF CO3 has been tested in the desert, even in California, where sometimes we have fires and polluted air. Keep in mind that the MOF itself is a filter, is a molecular filter. So the pore size does not allow very large molecules to go in, perhaps just water and CO2, but water binds stronger than CO2, so CO2 cannot hang around. I think down the road, if indeed there's dust complications, you can always use filters, like the filters that are used in your car to filter the air. So but we have not seen any complications from the particulates or anything like that. And we've gone through, I said 30,000 cycles, but water harvesting will tell you that they've done it 65,000 cycles. So with complete reproducibility.
Okay, thank you.
You're welcome.
Joachim Sauer has a question.
Then Joachim Sauer first.
So, Omar, you showed this multivariate MOFs and you made this comparison with the enzyme, that you also have there many different pieces. But there is an important difference. In the enzyme is very well organized. It's completely defined. While in your multivariate environment, it is kind of statistical. So, what are your thoughts about that, about this difference?
Good question. First, I want to just say that if you try to design a pocket like an enzyme, which many people have tried, it's not so easy. Okay, the enzyme behaves the way it does because it evolved into being what it is. Okay, so let's remove from our mind any kind of notion that we can mimic the structure of the enzyme. So what's the next best thing? The next best thing is to also remove from our mind the linearity of how chemists usually will think about making stuff. We like to make stuff, characterize it fully, then use it. And what I am saying is that I'm going to make the stuff partly characterized because you know the backbone very well. You know the metrics of the system. We also know that it's not quite a statistical mixture from other experiments, from NMR experiments, that there are potentially domains that are dominated by certain functionalities. So there's biasing within the pores. But I'm not going to characterize the whole system because I don't have an enzyme that can go in and sequence the different functionalities and give me their spatial arrangement. But instead, what I want to do is I want to pick a property like cleaving this amide bond and then start varying the ratios of those functionalities in the pores. That you can do. You can deliberately change. In that example, you're doing reactions, but in other examples, you could actually introduce functionalities in given ratios. So you can control what functionalities are there. You can control what the ratio of functionalities, but you don't know their spatial arrangement. So now, to characterize the system, I need to go to function. And if I can pick a function like cleaving an amide bond, now I can use Joachim Sauer's computational methods and machine learning to work a sequence backwards, to correlate the properties that I'm seeing with potentially what kind of environment might I have inside the MOF. And that's what I'm saying. I think chemists need to change their frame of thinking when it comes to these multivariate systems, because the stuff that we might think is heterogeneous junk is actually an opportunity to have very selective reactions. Yeah.
Okay, thank you. Thank you very much. Karsten, are there questions from?
Yes, we have 3 questions in the chat. The first one is if you could briefly elaborate a bit on the potential of combining MOFs or also covalent organic frameworks with surfaces, as in SURMOFs.
There is a lot of very nice work done in Germany, actually, on making SURMOFs, on basically growing MOFs that we might grow in a crystal, but by growing those on a surface. That's already been demonstrated. I think with the COFs, there is some work where COFs have been, let's say, carbon-carbon bonded COFs have been made on a metal surface. The challenge is in both is getting enough area, covering area of those films. But we are able to make them on a, let's say, nanoscale, nanosize, even maybe a micron size. But we need to go into much larger areas to completely harness their function. So there's I think a contingency of researchers out there who are working in this area.
And then there's another question by Martus on the stability of COFs that are made from boronic acid in the presence of water. Is that?
Yeah, I mean, the boronic acid-based COFs are not so stable. You can't just let them sit in water. But the COFs that I showed you with the olefin, you can make them sit in water or acid or base. They are very, very stable. That's where we've graduated from the original COFs into these carbon-carbon bonded COFs, which are the ultimate. Yeah.
And then finally, we have Thomas Bein, who is very grateful for your beautiful lecture. And he asks about your knowledge on the impact of the thermal conductivity of the MOFs, especially in the process of the water harvesting.
Yeah, so they're not, MOFs in general are not thermally conductive and are not very good thermal conductors. We have not, so what you're doing there with many of these systems is that you're trying to make coatings of the MOF, and the coating is blended with polymers. So far we have not necessarily seen anything that, and also you have to heat the MOF up to, like I said, 40 to 45 degrees in some cases, in other cases where you want fast cycles, up to 65 degrees Celsius to remove the water. We have not seen any complications because of the thermal conductivity of MOFs. I mean, they are conductive, but they're not very good thermal conductors, but it's not a problem. It is something, Thomas, it is something that you have to put in your models once you have the system as a whole. These things have to be, or are being modeled, put into those models.
Okay, thank you very much. I think there are no more questions in the chat. Is there still one? Okay, I'm sorry.
There would be one last question, maybe, just because it's already there. I think it would be fair to bring it. Pooja Singhvi asked if you have ever thought about encapsulating a MOF in an artificial semi-permeable membrane, like a phospholipid bilayer, to selectively allow water to enter into MOF pores as a filter. So it's a very specific question.
Yeah, I mean, MOFs have been incorporated into membrane, industrial membranes as well as liposomes type of things. But in this particular case, I mean, you don't need it. The MOF is already seeking out the water and trapping it. Yeah, but I can imagine that you can include fragments of MOFs in membranes and try to do what, like aquaporin, for example, the biological systems, how water can be transported and ions.
Okay, thank you. I think with that we have come at the end of today's lecture and questioning round. I don't see any more questions right now. So I would like to close today's session. Omar, I would like to thank you once more very, very much. And I do this on behalf of the Berlin universities, on behalf of the Fritz-Haber-Institut, on behalf of UNISYSCAT, and on behalf of BASF, and very explicitly also on behalf of Gerhard Ertl. Thank you very much for your brilliant presentation. It is one of those topics and one of those presentations when I'm listening to that, you think, what am I doing myself, right? And it will really lead to a lot of discussions and a lot of thinking in the days to come. I would also like to thank all of you who joined today, who participated in the opening words and so on. And with that, I am going to close. I wish you all good day. Yes, it was unfortunate that we could not meet in person here, but in this way, we indeed probably reach more people than we would have been able to reach in the lecture hall here around the corner, certainly with the rules that we have now for limited attendance in those lecture halls. So again, thank you all very much, and hope to see you all next year. Bye-bye.
Thank you. Thank you all. Thank you.